We are live.
Hi, good morning, everyone. Welcome to LESA's virtual Industry Academia Day. Traditionally held in the spring, IADays is our version of an annual open house with the aim of bridging the gap between academic research, innovation, and market expectations with our industry partners. IADays is normally a two-day event where we share our research and innovation in our 5 main research verticals: smart buildings, human factor studies, VLC communications, cognition through AI machine learning and AR/VR capabilities, and plant science with regards to cyber-physical farming and controlled environment agriculture, and our competencies around advanced sensors, autonomous control, and the built environment. The presentations today will be recorded and made available for our industry partners as part of their LESA Center membership benefit. We'll go ahead and get started. And for those of you who don't know me, my name is Leah Scott, and I am the Marketing and Outreach Manager at LESA. Today, you will also hear from our Program Manager, Michelle Simcolet, and we have Lindsay and John helping out with support in the background. The formation of the new Institute for Energy, the Built Environment, and Smart Systems, or EBUS, was recently announced by Rensselaer President Dr. Shirley Ann Jackson at Rensselaer's response to President Joe Biden's call for climate action. Though initial framework for the collaboration between LESA and CASE has been in the works for a while, EBUS fuses architectural design and engineering to create sustainable infrastructure through the use of renewable energy systems, sentient building platforms, and new materials. Our speakers today are going to be Robert F. Karlasik Jr., who is the Director of the Lighting Enabled Systems and Applications Center, or LESA, headquartered at Rensselaer Polytechnic Institute in Troy, New York, and Dennis Sheldon, who is the director of the CASE Center for Architectural Science and Ecology, or CASE, located in New York City. And he is the associate professor in the School of Architecture. I will now turn the presentation over to Bob Karlasik to present on EBUS. Bob, we're ready when you are.
Okay. Well, I'd like to welcome everybody to our mini industry days. This is a little different than what we've done in the past. And for those of you who have been familiar with LESA's industry days, they've usually been held live, presentations from a mix of faculty and students, poster sessions, and a lot of interaction with our industry members. Unfortunately, this year, we're just recovering from the pandemic. And so we're going to have something a little bit different today. And we're going to be focusing on the programs that we've got going on as presented by the students. So you get to hear from the people who are really doing the work, what we have going on. And as usual, our funding organizations are represented by the organizations you see on the left-hand side, the National Science Foundation and the State of New York, 2 organizations from the Department of Energy, and we have a consortium with Cornell University that we call GLAZE, where we work on advanced systems for plant, lighting, and horticulture. And over on the right-hand side of this slide, we have our traditional Pentagon. We're upgrading that now because we're moving into the future with some new interactions that are going to allow us to really focus on autonomous intelligent systems. And I'd like to describe a little bit on the next slide, just to set the tone so you know where LESA is going to be heading in the future. So what you see on the left-hand side of this slide is our same Pentagon, if you will, of our key focal points in the research that we're doing. Visible light communications, or Li-Fi, has now become beyond 5G. Many pundits in the high data rate communication space feel that RF will not be enough, especially inside smart buildings of the future, to provide equitable bandwidth for everybody who wants to be able to participate in the information revolution, especially as IoT and AIoT come online. That's followed by what we used to call cognition, which is really now more focused on machine learning and artificial intelligence. How do we convert a ton of data to actionable information and even wisdom with regard to how that applies to the built environment and other systems like horticulture? That transfers to what used to be called efficient buildings. We're now really moving into more of what we call sentient buildings. the building can actually know where its people are and estimate what they're doing and manage their wellness, manage building energy consumption, and so on. Of course, we're very interested in intelligent ag. We're mostly here at RPI focused on the sensing systems and the control systems that we need to have to be able to really improve agricultural outcomes. And that is something that we're really excited about and looking to continue to grow in the center. And then finally, wellness. Those of you who know the center know that we've been focusing on lighting and circadian control. But as we move into well buildings, we're going to be looking at indoor air quality, sensing systems that will allow us to manage that and have it to interface to a whole host of other building services. And then that really becomes how do we actually put all this together? So we'll have a lot of sensors, including biometrics, plant metrics, building metrics, and we'll be moving outside of simple light-based sensors into chemical sensors, RF-based sensors, in the case of plants, even terahertz-based sensors. And then we want to convert that information directly into actionable information for smart cities of the future, where smart rooms get parlayed into smart buildings that talk to each other in smart urban environments that are energy efficient, sustainable, and have a much lower carbon footprint than in the past. So today you'll get a chance to hear our students talk about the things that they are doing. And if you'll take a look at the next slide, I want to just say a really quick word about EBIS. You've heard about it already. It's actually a combination of LESA and CASE, but a lot of other research centers at RPI that are going to be working together on the smart connected city space. The centers are also going to be working with industry members and strategic partners as we put together this institute. Dennis will say more about it. And so what I'd like to be able to do is to move to Professor Dennis Sheldon. He is the director of CASE and a professor in the School of Architecture. I have the pleasure of working with him and his team in the School of Architecture to develop new modes of collaborative research. And so Dennis, take it away.
Yep, great, thanks. We made it. Yep, and I'm just going to really quickly go next. We're really excited to be working more formally with LESA under this new banner of EBIS. The fact is, LESA and CASE have been tight collaborators on numerous projects since before my time. I'm fairly new as of the beginning of 2020, but my colleague Alexandra Samas, Joseph Draper, and many others have been strong collaborators with Bob and his team for a long time. So, I'll show you just a little bit of the vision of CASE and then talk about where we think EBIS is headed. But CASE is much more, I would say, at the application side of things and less at kind of the core technology development. Our ambition is really, we come from architecture and kind of integrated solution development. And so this just to me is kind of the image of the kind of problems we're trying to tackle in the world: large scale inhabitation systems, materials. How do we put a greater and greater number of people on the planet and actually reduce our footprint? Next. So just some of the themes of the history of CASE. There's been a very sort of world-class trajectory around building system development. I think a lot of the signature projects have been sort of at the skin, smart skin, green walls, interactive walls, alternative uses of new materials, et cetera. But it's that kind of aesthetic and sort of mission that's been a part of the heritage for the last decade. Next. And just some of the themes again, consumption of resources. How do we build the inhabitation footprint of the planet without the sort of destruction both at the actual kind of building level, but also in the supply chain. Next. It might be a little bit higher. Yeah. So again, kind of new uses of materials. A lot of what we're trying to do actually is repurposing of or what you call upcycling of materials. Some coming from agriculture, some coming from food waste, and rethinking kind of how we use materials in kind of smarter ways. Also applying technology such as 3D printing, but again, less sort of toxic and more and less energy and toxin-intensive materials. Next. And then, I think what I bring, without spending too much time on my background, but I actually come from kind of the intersection of the architecture and tech world. So to me, of course, data is a significant piece of what Bob's and LESA systems provide. How do we make use of that, integrate that into design, build, operate systems, and take advantage of it to understand kind of what's going on at the building level, at the planetary level, at the city level. Next. And then I think, this idea of the digital twin, or sometimes called cyber physical systems, is really central to kind of the future mission of CASE, LESA, and EBIS, that we can sort of go not just bidirectionally in terms of data, but sort of use this sort of principle of systems and integrated physical and digital to develop these kind of integrated cyber physical systems from day one, so that the information and the material and system organizations are fully synthetically integrated, from the beginning of design through operations. Next. And then some of the things, again, that come from the tech world, we're not just doing this to just as a kind of a functional aspect of society. We're actually sort of trying to kind of figure out what the next generation of living in the world looks like. And I think that's really central. There are important questions when we start sensorizing the planet, which is, aside from just making buildings work better, how do people interact with these new worlds? And, this idea of sort of hybrid or mixed reality, how do those kind of technologies integrate into the built environment directly? Next. Just really quickly about the programs. We have kind of 3 core Master of Science and PhD level programs. The Built Ecologies program has been sort of the traditional anchor of CASE. There's been a kind of a parallel program called GeoFutures, which is much more kind of at the urban level scale, and the sort of the critical side of how do we think about urban environments. And then I'm bringing, from my background, more of a kind of a focus on the software and data side of things through the design tech program. Next. And then the last piece is, how do we engage with the world in new ways and new innovative ways, which to me means we have to look at the practice and the business of delivering innovation, delivering buildings into the world. And we have very strong interest in the application and bringing students and perhaps companies together to think about either, spin-off companies or incubators, but just, how do we build differently, not just in terms of the physical components, but really in terms of the collaboration and the outcomes. Next. So, just really quickly, EBIS got formally launched 2 months ago, and there is a really, great, I think, synergy between the work of LESA at the device level, at the kind of the energy and application level, at the lighting level, and then, so again, sort of more of these kind of system and application components. Next. We were very honored to have the launch of EBIS announced at the Biden Global Leaders Summit on Climate by our president, and we are now sort of going through the process over the summer to really kind of launch the programs, and frankly, that's where people, from this audience, are gonna, we hope to engage you guys over the summer, going into the fall, and over the next year as we build out our industrial member programs, and work with you guys to help us define the mission and the actual project that we're going to take on. So I think that's all I have. Again, I'm delighted to be in front of you guys the first time. I hope it won't be the last time, and I'll turn it back over to you, Bob.
Okay, thank you, Dennis. And I think that what I'd like to be able to suggest is that because we're wanting to be able to answer questions you might have about EBIS and CASE and where things are going to be going, let me ask Lee if we can take a couple of minutes before we get to the students to see if I have any questions from the chat running so far. And then, Dennis, I wanted to ask you a question and also make a comment about EBIS as well. So do we have any questions from the audience yet in terms of Q&A for either Dennis or myself?
So if you are in the audience and you'd like to ask a Q&A, please enter those questions into the Q&A box. You should find that next to your chat box. We're going to use the Q&A box, and we will read those aloud for either Dennis or Bob to answer those.
Okay, so because some of our people on the attendees weren't necessarily asking questions right away, we're still in the program. Dennis, let me take this opportunity to ask you a question really quick. One of the things that I have found very interesting in my conversations with you about your vision for CASE and the built environment is what your view is of the transformation of the building industry. How do we make buildings? How do we install buildings? Where are we going to be headed in terms of transforming how the construction industry is going to address buildings of the future sustainably and with energy efficiency in mind?
Yeah, absolutely. So, I mean, I think, underpinning all of this is the fact that the the building industry is still quite a traditional industry. The kind of formal structures of design, bid, build, operate, those kind of stakeholders and what they do has not evolved since, the early 20th century, let's say. And if you look at other industries that have been become much more integrated and have taken on, bigger and bigger opportunities for innovation, things like, the aerospace and manufacturing and automotive industries, this idea of sort of integrated product life cycle is one of the kind of drivers from a technology perspective. But I think, so part of it is really sort of rethinking the business organizations of the stakeholders in undertaking buildings. There's tremendous innovation happening now in terms of manufactured buildings, which I think also kind of unleash a lot of potential for innovation and integration, and that sort of move to manufacturing, more high precision, and will allow, and really sort of removing what's called, what you might think of as the friction in the built environment between stakeholders, where errors and actually, loss and sort of, lowest common denominator kind of efforts happen. So I think, again, while we're all working on the technologies, both at the kind of the device level, the system level, there's a very much a parallel kind of process and business organization level that's needed to happen, and it's happening now, right? So much more manufacturing offsite, much more kind of looking at things as kits of parts, hot swappable components, and then the data platforms themselves that can allow this kind of integration of data, process, and performance, again, as kind of an integrated part, both of the processes and of the systems themselves.
Yeah, I think that's really an exciting viewpoint of how we really take a look at driving the future forward. And as I mentioned at the very beginning, EBIS is more than just CASE and LESA. It gives us the opportunity to reach out to other experts on campus and other centers as well, to engage global experts in machine learning and artificial intelligence, in big data analytics, in sustainability and advanced material science, transportation systems and supply chain management, and economics. And so all of these other centers and their expertise will be able to fold into EBIS as we focus on bringing this more broad expertise into the development of the EBIS platform. Dennis, let me put you on the spot and ask one more question. Who are you most excited, besides LESA, of course, who are you most excited working with on campus of people that are outside of the CASE LESA family right now in terms of what you see great opportunities for?
Yeah, that is putting me on the spot. I mean, there's so many great people that and I'm just starting to learn kind of where all the players are. But the Future Energy Systems programs, the advanced manufacturing programs. We have a kind of an emerging partnership in New York City with Brooklyn Law School, which again will help us at kind of the entrepreneurship and policy level, because we need to change policies around how buildings are specified and delivered. We're looking at this relationship with Mount Sinai around kind of healthy living. And then there's really interesting stuff. Certainly at the data side, we have one of the strongest kind of data and ontology programs on the planet. And then also there's some really exciting stuff at the kind of the what you might call the product design level. But I'm continuing to learn about people all the time. I would even mention the Jefferson project with their approach to sensorizing water, the water resources of the planet, and then even this idea of kind of new vertical transport around smart personal drones and things like that. So as we like to say, it really is a polytechnic ambition, and I think that's what the framework of EBIS will allow us to do institute-wide, is really sort of develop those synergies and develop projects and bring them together with our industrial partners to develop focused ambitions and focused initiatives across all of that kind of huge spectrum of domains that impact the built environment.
Great, Dennis, thank you. And I should mention that one of the things that we're going to be exploring over the next several months is expanding the E in EBIS and taking a look at energy opportunities. A lot of the built environment energy opportunities are going to be based on renewable energy, smart grid connectivity, grid connected buildings. But beyond that, we want to start taking a look at other advanced energy systems, including green hydrogen. We have people at RPI that are looking at those kinds of technologies. And we also have a lot of industry members that are starting to kick the tires of both LESA and CASE, as well as EBIS, that are very interested in taking a look at how things like green hydrogen will integrate to urban built environments of the future. So with that, I think we're getting close to the time where we want to kick off our student presentations. I'm
Bob
really
and Dennis, we
do
have a question from the audience for you. We have one question. How will engineering education have to change to meet this push for manufactured construction?
Great question. Dennis, you want to take a stab at that?
Yeah, I mean, I'm not sure if this is a one size fits all, but clearly, I mean, there is a move in engineering and business and many other sectors to look at, design thinking, right? And I think that's really one thing that CASE and architecture and things like industrial design bring to the table is, we can sort of just breaking down problems into their constituent parts and solving those parts, sort of, I don't want to mischaracterize engineering, but, sort of in isolation, that's not what's going to allow the kind of the transformation that's needed across some of these wicked problems, right? So I do think that kind of the evolution in engineering toward both analysis, but also synthesis is a critical piece of it. And then, everybody's got to understand the data side of things, and and how we kind of iterate with the world, because our first assumptions about what engineered systems need to look like, needs to evolve as they actually hit the planet. How do we do that in a more agile and quicker and richer way? I think those are two important kind of directions for engineering education.
Yeah, and let me emphasize that. I think interdisciplinarity is going to become much more important in engineering, factoring in humanities and arts and social sciences in engineering, and also thinking outside of the chip and the packaged electronic circuit. How do I put basic kind of sensor technologies directly into buildings, directly into materials? How do I assemble them? What's the role of robotics in building buildings? How can we 3D print buildings? These are the kinds of interdisciplinary things that we really need to focus on. That's going to be a cornerstone of transforming pedagogy in the School of Engineering with regard to making it reach out well beyond itself. And that's one of the real pleasures of being able to connect to the School of Architecture and take a look at how we can complement each other in terms of that interdisciplinary thinking and education of engineers of the future. So I hope that answers the question.
Okay, Leah, we are out of questions.
Okay. Okay. So Michelle, we can move ahead. Great. Dennis, Bob, thank you so much for that overview. It's really insightful, and there will be more information forthcoming about how EBIS shapes up in the next few months. So stay tuned for that. Without further ado, we'll move into our student perfect pitch sessions. The perfect pitch was created at LESA by the former director of industry relations. The perfect pitch was broadly adopted by the National Science Foundation as a requirement for ERCs. For those of you who don't know, LESA is a graduated ERC. And as many of you may remember, the perfect pitch presentation at previous IAD days has had a tremendously positive impact as a training ground for our students. This year, we decided to revive the perfect pitch as a way to once again bring industry and academia together as we continue to observe the Rensselaer community's COVID-19 guidelines. The virtual perfect pitch session will feature both LESA and CASE's exceptional student researchers in a one-slide, 90-second elevator pitch style presentation covering topics related to smart and sustainable systems integration with modern applications in the built environment, advanced sensors, and autonomous control. Not only is this exercise important for our students' professional development, but it is a competition for them to have a chance to win a cash prize in the amounts of $300, $200, and $100 for first, second, and third prizes respectively. The official winners will be announced tomorrow via our social media channels and our website. So if you haven't liked or subscribed to them, please do so from the LESA website. I'll go ahead and introduce our judges. We have with us Josh Draper. Josh is an architectural designer who works at the intersection of computation and craft with broad experiences in digital fabrication, computational design, and rapid prototyping. Josh is a lecturer at Rensselaer Center for Architectural Science and Ecology, or CASE, where he teaches research methods, material systems, and design studio class. We also have John Erickson. John has spent over 2 decades studying the unique social, legal, and technological problems that arise when managing and disseminating information in the digital environment. He currently serves as Director of Research and Operations at Rensselaer's Institute for Data Exploration and Applications, or IDEA, and the Deputy Director of the Web Science Research Center of the Tetherless World Constellation at Rensselaer Polytechnic Institute. I'm also pleased to introduce Kelly Reardon-Sleeker. Kelly is an Associate Program Director at the Severino Center for Technology Entrepreneurship at the Lally School of Business, where she helps students develop skills and knowledge necessary to deliver validated products and services to market. She has coached over hundreds of student teams to pitch their businesses and is uniquely qualified to weigh in on the broader impacts of commercialization of the presentations. And we have with us Diane Viros. Diane has over 30 years of experience administering large and complex research centers. She previously served as the Director of Operations and Finance at LESA before retiring in 2019. She has experience in strategic planning, grant and contract management, budget and financial management, and establishing policies and operations to ensure compliance with sponsors and university regulations. I'd like to give a thanks to our judges for giving their time to us and evaluating the presentations. After each pitch, there will be a 2-minute pause for the judges to score their performances. For everyone else, we have prepared a few slides and videos to keep you engaged, so don't worry. After each group, we will have a brief Q&A for those wanting to ask questions. Questions can be dropped into the Q&A channel, just as before, from the menu at the bottom of your WebEx screen. The questions will be read aloud and should include the name of the student you are asking. In addition, the industry attendees will have the opportunity to vote for their favorite presenter for an additional $50 for Best in Show. And I'll have more details about that as we get towards the end of our program. So without further ado, we'll go ahead and move into our student pitches. So with us, we have group 1 for advanced sensing from designers to implementation. We have John Rawlinson, Xing Tong, Hao Lu, and Jason Case, who accepted an internship last minute and pre-recorded his presentation. So we won't be able to have direct Q&A with him, but we are certainly able to direct questions to him as we're still in contact. So John, whenever you're ready, unmute and we'll begin.
Okay. Good morning, everyone. My name is John Rawlinson, and today I'm going to talk about the scalability of integrated photonic components. So over the past few decades, we've seen photonic systems scale from bench-scale laboratory demonstrations to chip-scale devices enabled by advances in semiconductor processing technology, which has allowed the co-integration of both electronic and photonic components. However, unlike digital circuits, which often integrate many millions of devices onto a single chip, photonic integrated circuits are often limited to, at most, maybe tens to maybe hundreds of components per chip due to physical limitations on device size. So our approach to this device sizing barrier is simple. Abandon traditional device design techniques and let the computer do the heavy lifting, using established numerical optimization techniques to accomplish this task. In this method, we define our photonic device as a black box, the shape of which is defined by some fixed number of parameters. An optimization algorithm then selectively varies these parameters, attempting to converge to an optimal design. This technique allows us to rapidly and efficiently search a design space for optimal solutions. And what's fascinating about this technique is how it leads to designs which could not easily be conceived of or formalized by a designer, and yet are more efficient and more compact than could be designed through theory alone. So using this technique, we've designed a photonic waveguide taper with an 85% reduction in device area and no loss of efficiency. And while this is a relatively simple example, this technique is extensible to enable not only more compact devices, but also more efficient devices and even devices with functionalities which were not previously achievable. Thank you.
Thank you so much, John. We'll go ahead and move forward. Xing-Tong, we're going to have just a few minutes for the judges to score John's presentation, so I'll announce you shortly. Hey, Xing-Tong,
Yes.
we are ready when you are.
Okay. So good morning, everyone. My name is Xing Tong. Self-driving vehicle promise to revolutionize the way people travel, and environmental sensors such as light detection and ranging system or LiDAR are one of the key components. For different self-driving scenarios, the priorities on sensor specifications are different. When a car is cruising on a highway, the range of the sensor needs to be prioritized since a longer braking distance will be needed. On the other hand, when the car is self-parking, a fine resolution will be required, but a long range isn't needed. To accommodate these different requirements, the existing solution from Additive Revolution is to have multiple types of sensors for different scenarios. However, this could increase the cost introduce more systems that could fail and make the system harder to maintain. What our team proposed instead is to use custom-developed LiDAR sensors with range and resolution that can be reconfigured, depends on the task. To our best knowledge, our team is the first to develop a working prototype mixed signal IC that enables LiDAR to change the range and resolution, which has the potential to reduce the complexity and cost of self-driving systems and make their maintenance easier.
Thank you, Xingtong.
Thank you.
Next up, we'll hear from Hao Lu. Hao, we're ready when you are.
Yeah, I'm ready. Hello, everyone. My name is Hao, and my work is about indoor occupancy detection. I'm actually trying to let the building see the occupancy in it and know where they are. With this information, the building can save more energy and people in it can feel more comfortable. Instead of using the cameras, we use the time of flight sensor, which has only 16 pixels. It can naturally protect our privacy and easy for post estimation. We install the sensor in the key point of the room, and when people move into the field of view of our sensors, it can detect the position, their walking speed, their walking direction, and know they are standing or sitting or even falling down. And our system has many applications. For example, in commercial buildings, the HVAC system can save about 45% energy with the information of occupants. And in senior nursing or home care, our system can detect whether this patient is struggling sitting up or falling down. And the nurse can use this information to protect the dangers happen to our patient. This is my work. Thank you.
Thank you, Hao. Next, we'll hear the recording from Jason Case, who accepted an internship and couldn't attend.
Hello, my name is Jason Case, and my research is on efficient health monitoring via body sensor network. Since the advent of mobile health monitoring devices, medical professionals have leveraged the advantages of wearable, mobile patient monitoring to research and monitor symptoms which may be intermittent or erratic, such as arrhythmia. Here on the left, we see recent advancements in the state-of-the-art of EKG monitoring. With the push towards telemedicine, which has been amplified by the pandemic, there's a need to extend this type of monitoring to body parameters, to other body parameters, some of which are shown on the right. Our research aims to apply a low-power analog front-end IC designed here at RPI to efficiently and wirelessly monitor multiple body parameters. A key focus of this research will be the establishment of an efficient, safe communication from sensor patch to a central node such as a smartwatch via a wireless signal which is coupled through the skin. This body-coupled communication has potential to reduce power requirements for sensor patches, allowing smaller and longer-lasting monitoring devices. This will allow patients to maintain a more normal lifestyle during their health monitoring. Thank you.
Thank you so much. We'll go ahead and take Q&A for our three speakers. And again, if you have questions for Jason Case, you can email Michelle or I, and we will forward those on to him. But please enter your Q&A into the Q&A drop-down box, and we will have Michelle read those and answer them.
I don't currently have any questions, so please, audience, feel free to add your questions, or students on the panelists, please feel free to unmute and ask questions.
Well, Michelle, this is Bob. Can you hear me?
Yes, I can.
Okay, then I'll ask one of my questions. And this question is going to be directed toward a couple of the students. The first one for John Rawlinson. And John, you know, you're talking about some rather sophisticated optical modeling of, you know, silicon fabrication technology. From your perspective, how do you see your research impacting the future of sensor chip manufacturing? What do you see as evolving technologies that make this a really fascinating area of sensory silicon?
Yeah, I think the technique is very broad in that it can be really applied to any integrated photonic component. I think one of the ways that it's going to be most important is that, especially for integrated photonic sensors, where we're really concerned about the efficiency of the device and operating in a low power mode, I think these kinds of optimization techniques are going to be very critical for getting the most efficient device that we possibly can and sort of operating at the lowest power point possible, as well as increasing sort of the density of the device. So we could say fit more pixels on a time of flight sensor or something like that. So I would say definitely in terms of density and power efficiency for photonic sensors is where it's going to be most critical.
Okay, thanks. And Michelle, any other questions from our attendees yet?
Yes, I have a question for Xing. So the question is, it says about LiDAR, from a technical perspective, how would the LiDAR technology be adopted for enclosed spaces? Would it be the same as for vehicles? Do you know what the challenges would be?
So using LiDAR for indoor sensing, I think in general is known to be easier than using it for autonomous driving, since like when you use LiDAR for indoor sensing, you don't need to be as concerned about like noise such as sunlight, and just the environment in general is more controlled. Whereas when you put the LiDAR in a car, you have to face all sort of environmental factors. So I think in general, if a technology would work for autonomous vehicle, it would certainly be very easy to adapt it for indoor sensing. So it's actually very challenging the other way around. When it works for indoor sensing, and when you try to adapt it to outdoor sensing, such as autonomous driving, it will be very difficult, since you have to deal with all kind of additional environment noise. So yeah, like I think like if a technology works well for autonomous driving, it's very easy to adopt it for enclosed spaces, well-controlled environment.
Okay, great. Thank you, Xing. I have a question for Hao. Can you please elaborate on the privacy features of your proposal?
Is protected by the nature of our sensor. It has only 16 pixels. So none of the profile of a person can be detected or recognized from the sensor itself. So it's naturally protect our privacy.
Okay, thank you, Hao. I currently don't have any additional questions. Any more from the panelists?
Or any questions from the judges?
Yeah, hi. This is Josh Draper. I wonder, did you work with each other when you were developing these proposals?
Well, we all work on the same project, but we didn't work on the actual pitches themselves. Yeah.
So you're working, okay, so you're all working together. And how do you, I mean, at a higher level, how do you see your solutions potentially integrating with each other? Is there a way in which there's a way that what you're each developing could impact or enhance what you're doing? So how do you see it in a bigger picture?
Well, I guess I can answer this question, since my work is a big picture for all this situation. And my work, one of the important part of my work is about the sensor. So I want the sensor has more range and more accuracy for the detection, less noisy, no effect from the sunlight. So the work from the Xing, and his LiDAR can give us another solution instead of the time of flight sensor I use right now, which is very sensitive to the sunlight. And also drone can give us the sensor with more range detection and more resolution of the time of flight sensor. If the time of flight sensor can have maybe 64 pixels, and it still can protect our privacy very well, but it can have a better location accuracy, and can distinguish different multiple persons standing closely under the field of view of the sensor.
Okay.
Okay, I have another question. Is there a conflict with the privacy through limited pixels that Hal mentions versus the work John is working on to produce higher density sensors? Or is the density still assumed to be too low to affect the privacy assumptions?
Yeah. The time of flight sensor is a depth sensor. It can only give you the information of the distance. So it only, even if it has infinity resolution, it can hardly detect who you are without the RGB color information. And one step back, our resolution is only 16 pixel. It's too low to see anything. Even if it's bigger into 500 pixel, it still really cannot distinguish different people with their face or even any shape of the body.
So I know this question is directed towards John and Hao, but I just want to jump in and say that, so increasing pixel density, another way to think of increasing pixel density is that on the same area of silicon, we can create more chips. Right? So if we want to fix the number of pixels, what we're actually doing is to reduce the area. So on the same silicon wafer, with the same cost, we can create more sensors. So that's what John is doing can effectively reduce the cost of the system. So the conflict between increasing the pixel density and privacy doesn't necessarily exist like on that aspect.
Yeah, I don't know if I have too much more to add to that other than that it's really more so on the algorithm side than the physical device side. As Hal pointed out, the device really has no knowledge of what's underneath it other than just the distance to the object underneath. So I think with the state of the art for machine learning algorithms, it's really not sufficient data to really identify a person other than saying that it is or it isn't a person.
Okay, great. Thank you all three for some great discussion, some great answers. Thank you to the audience for some engaging questions. Any other questions from the panelists before we move on? Okay, Leah.
Okay, we'll go ahead and move forward with our second group, autonomous control impacting the human experience. We'll hear from Lingyu Zhao and Konstantina Versamai, Pranav Shasasi, and Daneko Bomuk. Lingyu, whenever you're ready.
Yeah, I'm ready. Oh, hi. My name is Lin Yu. My research focuses on multimodal deep learning for video question answering. One example for our problem is that giving a video about some girls trying makeup products on their faces, there is the question about the reaction of the girl when the other girl starts feeling pain. So our model needs to read the video and understand the semantics in the question to select the correct answer from a multiple choice list. So we can see that the appearance, interaction, and motion, the timing and order of different events are very important. So for our method, we use convolutional neural network to extract visual features in each video frame. We use BERT to encode each word in the question as a vector. We design a recurrent neural network to capture the temporal dependencies and pay more attention to certain timestamps to better capture the key information. Timestamps here with the darker color means we pay more attention to them. So we compare the similarity between the answer and the given materials. We will select the one with higher similarity score as our final choice. Our model can be used for many real-world applications. For surveillance video, by asking questions like, is there any suspicious behaviors? We can take quick actions. And by automatic question answering, we can understand the education material efficiently, do reasoning about group interaction dynamics, and evaluate the quality of the advertisement. Thank you very much.
Thank you so much. Constantina, we are ready when you are. Constantina, you'll need to unmute. Just start again.
Okay, thank you. So after watching the movie AlphaGo, the software program that created a world champion in the game of Go, questions about the interrelation of human with artificial intelligence emerged in my mind. And unlike AlphaGo, many more computer programs have competed successfully against humans over time. However, what all those approaches have in common is the idea of human intelligence competing against artificial intelligence. And having realized that, my thoughts focused on the alternative. What would happen if advanced learning systems were to collaborate with humans? That is what I attempt to describe with the term collaboration, an advanced mode of interaction between humans and artificial intelligence systems that facilitates bidirectional communication. Hence, light is examined as the mediating interface for collaboration, an interface that has already been extensively used to improve user well-being. From my perspective, my goal is to design human lighting interactions, to develop intelligent lighting control algorithms within the built environment that dynamically regulate lighting based on occupant activity. And to do so, physical and virtual lighting systems need to be developed in parallel to afford effective design and efficient visualization of lighting scenarios. By integrating those two, the resulting system will be able to learn from its environment and predict occupants' needs, promoting more intuitive and collaborative interactions with humans. So all in all, since this integrated system dynamically regulates activity-tailored lighting, bidirectional communication, and intuitive interactions with humans are achieved, collectively promoting the concept of collaboration. Thank you.
Thank you, Constantina. All right, Pranav, we are ready when you are.
Good afternoon, everyone. I'm Pranav Shrestha. To deliver light when you need it and where you need it, occupants' behavior ought to be considered. This includes gauging participation of individuals at any given time. Participation between individuals reflect real-life interactions that are dynamic and ever-changing. Therefore, we must consider the behavior of multiple bodies in a room and their participation with each other. While a substantial amount of data is available, mostly for isolated individual actions, there's still a lack of data representing larger group interactions. For this reason, it is quite a challenge to develop machine learning models for group activity recognition. We introduce AI navigation in Game Engine that allow us to circumvent this problem by using realistic synthetic actors that have the same skeletal format as the real body tracker in the physical testbed. In our digital twin, we have scheduled multiple scenes of different group activities randomly throughout the week. Notably, all that occupant data can be retrieved in less than an hour. This is a considerable step forward in developing an accurate group interaction metric system, including engagement and leadership indices of individuals in the space. Now, based on the group behavior as well as individual needs, we can deliver proper circadian dosage or even create alerting effects to the occupants in the room. As a result, we can sculpt energy saving, health conscious, and task specific lighting.
Thank you, Pranav. Dianco, we're ready when you are.
Sure. Good morning, everyone. My name is Dianco, and I'm going to talk about control of light using backlighting drivers. Imagine a scenario where you enter a room and all of the lights in the room turn on and direct light based on whatever you or anyone else is doing in that room at that particular moment. This is something that researchers have tried to solve for quite some time now. But there does not exist any robust control system that can control such sculpted light across multiple luminaires in real time. What we are trying to do here is to use backlighting drivers, which are generally used for HDR displays, and use them to control light in multiple luminaires consisting of many LEDs. We can use multiple of such drivers to control the intensity of light, the angle at which the light is being projected, and also the color temperature. We can use advanced dimming techniques to smoothly change from one lighting scene to another without any abrupt changes. We hope to achieve all of this with complete autonomous behavior. If we can do all of this, we can achieve responsive light based on real-time human activity and occupancy. And it will also lead to saving a lot of energy in the long term, while also providing a higher quality of life for all of the occupants. Thank you.
Thank you so much. We'll go ahead and move into the Q&A. Michelle?
Yes, I have one question to start. This question is for Ling Yu. It says, very interesting research, but my question is, would you want the system you are developing watching you during a job interview? Why or why not? And what systems will be needed to protect privacy?
Oh, yes. So this is the very great question. So for example, during the interview, you want to analyze the performance of the interviewee, and you want to analyze the content. If you have this kind of AI like team member or AI interviewer to analyze everything like the interaction dynamics, and then this like sensor box can help you to like understand what happens during this video, but it is better than a human being is watching you, right? Because we can directly get some like inference result from our model instead of having a human to know what really happens in this video. So for the privacy, I think this model kind of help us to preserve this privacy, because we can directly get some result instead of know the extra things in this video.
Okay, thank you, Ling Yu. We have an additional question for Constantina. Do you see a future where a dynamic lighting system can be used to intentionally influence human behavior? And what would be an example of that?
Yeah. So basically, lighting can definitely affect human health and well-being, and therefore potentially behavior. So by regulating, for example, lighting has a potential as an output device that communicates information to humans. It has the potential to communicate information in the room and kind of like inform the human about things that are happening around him and that maybe he's not aware of. So given that, like, the human might be able to kind of interact this information flow, and therefore like change his behavior based on that.
Okay, thank you, Constantina. We continue to open the floor to questions to the audience. Please add your questions to the Q&A block for this panel. So I have a question for the panel. I know as a member of the center that you three work on the same project together. Can you talk a little bit about how you work together and interact based on the material that you presented here?
So I guess like from my perspective at least, I think like Pranav's work is oriented maybe around the human detection system, so recognizing like occupant position and identifying their activities and stuff, which feeds like if we think of it in the digital kind of mode, then it it can directly feed my virtual lighting system, informing about like the occupant position and therefore driving the dynamic sculpting of lighting. And then I think the Yanko's work is oriented more into the physical lighting system and the control algorithms that go there, and therefore controlling the physical aspect of it. But like, if you have like anything to add, please go ahead.
I think there's a bit where we're trying to visualize the humans that are in the physical testbed into the digital twin directly, and that part is also kind of the collaboration between Dianco and me walking on from here. But yeah.
Yeah, I guess that sums it up quite well. Like you could say the workflow goes from Konstantinos' work, then to Pranav's work, and then eventually my work, which realizes it in the physical space. So let's hope this can actually change the way lighting works.
Right. Ling Yu, a question for you. Would you see a potential for the lighting reactions to occupancy that the other three participants are working on? Do you see that a way that that could integrate into your work?
Yes, sure. So, for example, if our ultimate goal is to build a sensor box that capture the video and audio signal for each participant in a group meeting, and so this sensor box will help us to like improve the performance. So, for example, for the lighting conditions, or we can preset some questions like can we see each participant clearly, or like can each like participant like behave very like comfortable during the meeting? So we can preset several answers. So for example, we need to adjust the lighting condition, or we need to adjust some other environment like settings for them to better like interacting in this meeting. So if our sensor box answer this question, like we need to adjust some lighting conditions, so it can help us to do some quick actions based on the like they analyze the data.
Okay, great. Thank you, Ling Yu. So I have a question for Pranav. Do you think there is an occupant count limit to the accuracy of the sensing system you are using?
We're not using just one, but there are a couple. There is a estimation for about 4 to be used in this physical testbed. So unless the room occupancy limit is exceeded, I don't think there's a limit. Especially because we were generously provided these powerful PCs that can handle it at the moment. But when it's prototyped, it must be probably done in a more technically conservative way. At that point, we might have to think about the limitation there.
Okay, and I have a question. I'm guessing this is for Ling Yu, but John, you can correct me if I'm wrong. How to mediate the mediation, meaning how to teach the system how not to be overreactive and thus not be annoying.
So if the reaction means our sensor box to make useful suggestions for team members, we are considering some other ways to do the proposed suggestions. For example, our sensor box may not have any like audio signals to team members. So for example, we will not speak loudly, say you should speak talking and the other one should start talking. We are not doing this. Maybe one plan we are considering is we have some like lights, like different colors, for example, red, green, or yellow for each team member. So in this way, each team member will see its own light. For example, red light means you may need to consider start talking right now. And red light means you may need to consider stop talking and let others to see others' ideas. So in this way, it will not be very annoying during the team meeting. So this is our current plan.
Okay, great. Thank you. So Constantina, that question can be applied to your work as well. So how to mediate the mediation, meaning how to teach the system not to be overreactive and thus annoying to the occupant?
Yeah, so basically the lighting system so that's, for example, also the reason why we're making those simulations, because we get to test. So the videos like you saw after my presentation, that lights were turning on and off. We're not suggesting that this is like the optimal lighting behavior that we want, like lighting to react in every person's movement in the room. So in order to address this, we are thinking at this point of maybe like programming some delays, and therefore being able to realize that if a movement takes like this amount of time to be realized, maybe the system can just completely ignore it, or like some delays that would not would not have light reacting if somebody like just tries to exit the room during a presentation. So we might incorporate like some kind of time delays in the system that can or it can also have to do with the activity recognition. So some kind of activities being recognized and having light kind of highlighting that area or others not.
Okay, thank you. So Josh Draper, you said you have a question about automation and user control. Since you're a panelist, you can unmute yourself.
Sure. And this is directed maybe to Constantina, but to the group. You talked about collaboration, but there's also a strong drive towards automation. And how do you position and maybe critique the tension between automation and collaboration? How is a digital twin not just a simulation and representation, but an actual entity and system with which users might be in communication with and interacting with?
So I think it has to do with the feedback flow. So if like humans, for example, act, then their actions get detected by the system responds, and then humans sense the response. Then there's like a feedback flow that runs from humans to buildings, and then back to humans, and then back to buildings. And then this allows basically for bidirectional communication, and this is what collaboration attempts to describe. Now, if we remove some parts of this, so for example, augmenting the automation part of the system by having systems that did not recognize what activities humans are doing, but from data that they are fed, kind of predict by themselves what happens in the room without actually sensing the room, then this feedback flow is kind of interrupted and the automation of the system is augmented, but that does not necessarily mean that there's this collaboration happening. Actually, this interrupts the collaboration that was supposed to happen. And this is kind of like where automation takes over and kind of interrupts the collaborative mode between the human lighting and human building interactions.
That's very interesting, and maybe others answer, but I want to ask one follow-up question. COVID has shown us that remote working is here to stay, probably. How could we imagine your systems, this is sort of maybe more broadly, where a digital twin maybe is another way of thinking about remote work? Is there a way that what we're seeing happening is a way to be together, but not physically be together? Does it have any bearing on what we've lived through for the last year?
So, like, I guess that, yes, we can have like this second kind of reality where we interact through these virtual environments solely, but this doesn't necessarily mean that this will be connected to reality. It's maybe more of a parallel reality rather than an interaction between the environment, like the environment we act and interact like physically.
I was going to touch on the feedback loop idea, where it's not just the light we send to the humans in the space, but also you know, it could be shorter term indications like maybe red light. That seems a little harsh, but somewhat more apparent feedback for normal tasks, whereas it could also be a longer term, you know, creating an alerting effect idea in the physical space. But if people are not working in the physical space, they could still get the same kind of feedbacks if they join in the meeting through their virtual lenses and stuff and get the same kind of feedback then, or at least close to it would be a good way to connect those two parts together, I think.
Thanks, very interesting.
Okay. Michelle, do we have any other questions?
No more questions at this time.
Okay, we'll go ahead and move forward with our group 3. Thank you, everyone. So our group 3 is going to cover the built environment improvements through technology innovation. We have Will Pepe, Bumsu Park, and Asid Eshan Nakvi. And I hope I pronounced that right. I'm so sorry if I didn't. And we'll go ahead and get started. Will, as soon as you're ready.
Hi, everybody. Okay, so Americans spend 90% of their time indoors where air quality is so bad that it accounts for 4% of all death, not to mention costing billions in lost productivity and sick days. It's clear that mechanical filters in our HVAC systems are inadequate, plus they require regular replacement, which costs owners money and produces waste. At the same time, buildings account for nearly half of all US emissions. HVACs consume 35% of all building energy and are thus a key target area for reducing both energy consumption and utility costs for building owners. A typical building relies on outside plants and trees to make clean air, then mechanical systems add or remove heat before supplying it to people inside, shortly after exhausting that stale air, along with all the conditioning energy that was just invested in it. I am proposing the generation of clean air from within buildings using moss, an extremely robust and high surface area green plant. And the idea is that by balancing plant photosynthesis with human respiration, we no longer need to expend energy continuously conditioning outside air because we have an indoor fresh air supply. In addition to physical particulate filtration, the moss supports a microbiome that adsorbs and metabolizes VOCs, something HEPAs don't do very well. And where indoor and highly occupied spaces can be stuffy, high in CO2 and other pollutants, inhaling inside a building with biome would be like breathing inside of a forest, only one with temperature control and plumbing. In essence, a living desktop air filter, you can add or subtract as many biomes as you want and realize the energy and air quality improvements that suit your needs. Clean, highly oxygenated air makes people smarter and more creative, and with building energy savings of 10 to 30%, the return on investment for owners is likely to be swift. Thank you.
Bumsu, when you're ready.
Okay. Hello, everyone. My name is Bumsu Park, and today I'd like to talk about machine learning for passive heating and cooling control. I guess my previous presenter mentioned this, but HVAC systems account for up to a third of the total energy consumption related to building systems. While reducing HVAC operations may have a direct effect on the reduction of total energy consumption, this comes at a cost of discomfort for the people within the building. However, we don't actually take full advantage of passive elements such as solar heating, natural ventilation, or radiative cooling, which can all drastically reduce the overall energy consumption without any major compromises if used properly. Now, the question is, what exactly is the best control strategy, and how do we come up with this? Conventionally, we would have to design a model to understand the relative effect of each passive element on the system, which can either be too complex or inaccurate. In this approach, instead of defining a model, we can deploy a machine learning algorithm, more specifically reinforcement learning, where the agent learns through experience, like the way babies or dogs learn certain behaviors. Upon trial and error, the algorithm can figure out the best control strategy on its own, even without a complex model. This will help us achieve specific goals in terms of reducing energy consumption, and also provide a framework in various fields, ultimately leading to a cleaner and more enjoyable environment. Thank you.
Thank you. Austin, when you're ready.
Thank you. Hello, everyone. I'm Saeed Esanuzan Naqvi, and I'll be presenting my work titled Energy Efficient Indoor Climate Control in Multi-Unit Buildings. According to recent estimates, 75% of all electricity in the US is consumed within buildings. More specifically, heating and cooling loads account for 80% of all electricity used in residential buildings. Therefore, buildings are an integral part of the energy ecosystem. This ecosystem involves several stakeholders, such as building operations managers and grid operators, each with their own objectives that can be achieved by effectively controlling HVAC operations. Developing control policies for HVAC is challenging as it involves controlling multiple operational variables simultaneously, which can increase the complexity of control algorithms. Now, our research has been able to use the mathematical representation of the heating and cooling effects of the fluid circulating in HVAC to express the entire framework for controlling HVAC systems in terms of a single operational variable. We have used this framework to design control policies for buildings and reported potential financial savings of approximately 19%. We anticipate that our proposed control policies could significantly reduce utility bills while ensuring occupants' comfort. It could also help achieve the objectives of the various stakeholders in the energy ecosystem. It could also facilitate the building equipment provider in offering large-scale deployment of such customized building energy management systems, especially in buildings that have limited on-site computational resources. Thank you.
Thank you. And we'll go ahead and move into the Q&A, Michelle, when you're ready.
Okay, so we have a few questions to start. Will, a question for you. Do you envision your biome system to be more applicable to a commercial setting, a residential setting, or both?
So both. However, the way it gets implemented or the sort of benefits you're going to get out of it are going to be different, whether it's a commercial or a residential setting. So in a commercial buildings in the United States, at least, ASHRAE requires outside air ventilation. And my system is saving energy by essentially eliminating that outside air ventilation. In single family residential houses, there is no such requirement. So you won't realize those energy savings. However, you'll still realize air quality savings in both cases, as well as multifamily residential.
Okay, great. Thank you. For Bumsu, are the occupants' psychological and physiological factors taken into consideration in the machine learning control models?
Yes. So at the moment, psychological and physiological factors aren't directly considered, but the guidelines for temperature ranges in which people feel comfortable, actually provided by ASHRAE, I believe it stands for the American Society of Heating, Refrigerating, and Air Conditioning Engineers, is sort of used as a guideline to take into account that sort of comfortness for the occupants. But I mean, the decision process is sort of like, given a certain situation, what kind of action would you take? And in that situation, like, as long as you add factors like comfortness or psychological factors, I guess what I'm trying to say is it is possible to add these features in the future. It's just that at the moment, as of now, it's not really considered. The only factor that's considered is the temperature range.
Okay, thank you.
Thank you.
For Asen, what would the label on your single knob be?
It is the power consumed by individual units in a building. So generally, if you formulate a problem for thermal regulation in multi-unit buildings, you have to be mindful of the mass flow rate of the fluid in the HVAC system. You have to be mindful of the zonal temperatures in the building and the return temperatures of the fluid that's flowing. Here, what we're trying to do is that we are trying to fix we're trying to reduce the size of the problem. And we have been successful in doing that, as we have been able to express the entire problem in terms of a single control knob, which is the power consumed in achieving that particular thermal regulation for a particular unit.
Okay, thank you. So Will, another question for you. Why moss instead of other plants that have been tested in similar plant walls, including one that was at RPI in the CBIS building?
Right. So there are a number of reasons why moss, while it's extremely understudied, both for phytoremediation and in general in plant biology, may be a suitable alternative to higher or vascular plants. The first one is surface area. Moss has the highest leaf surface area index of essentially any plant. It's rivaled only in the natural world only by like pure peat or like soil. So extremely high surface area is very good for filters. It also has a very high photosynthetic surface area, which means it is capable of generating oxygen, even though it does photosynthesis slower than plants on a leaf basis, higher plants on a leaf basis. So that's one. The other is that they're extremely robust. They're among the first life to evolve out of the ocean and into terrestrial land. And so they are used to, they enjoy a high CO2 environment, and they don't really have very many life requirements. You can also change their lighting regimen without upsetting their circadian rhythms very much. And just in general, they are quite robust. So it supports this modular aspect, which is the real differentiator between the sort of CBIS and AMPS projects that were previously at CASE and RPI, which you need a construction project to essentially install those walls and integrate them physically into the HVAC. My system is a little different in that it's a modular air filter and it's wirelessly integrated into the HVAC. The moss, and you can move these systems around, and while that might upset a higher plant, mosses are not really going to care about that.
Can I ask a question too for Will?
Sure.
So can the moss go into existing buildings, or is this only, I'm sorry, I know I'm faint. Can the moss go into existing buildings, or do you have to build new? I mean,
right. So the idea is both. It's fundamentally an augmentation of an existing building, but you could easily build a building and right after you're done, put these units inside.
Does that mean that different parts of the same building could have the biome system and others not? Can it be heterogeneous within the same building?
Absolutely. So you essentially can create whatever kind of microclimate you want based on the placement of the units, and you could also, given the sort of given how fancy your HVAC system is, you could direct, say everybody has left their desk and gone into a conference room. You can take all the oxygen that's being made in the office space and direct it into that highly occupied conference room, or HVAC control regimens like this are possible.
and do you work with, I mean, this is plant kind of based, so do you work with people at the LESA Center in the plant department? Is that something that you would do to collaborate? I mean, that just sounds like a great collaboration opportunity. So.
Absolutely, that's actually where I am right now. I'm in LESA, and I've worked with Elizabeth Kolmos and also photosynthesis, and now characterizing pollutant decay curves.
Wonderful.
Okay, I have a question that goes to all three, and we can answer in the order that you presented. So Will, then Bumsu, then Asen. So will our built environment get to the point where they know too much?
Okay, an interesting and open-ended question, I think. In the context of my kind of project, the only sensors that are on the units are air quality sensors, and so you might be able to indirectly infer kind of occupancy levels and outdoor air quality. But in the case of air quality, I don't think there is such a thing as too much information, other than maybe it's difficult to store it all. But it would be good. The environment is in general undercharacterized. We don't really have a good idea about what the indoor microbiomes look like. We have a slightly better idea about what indoor pollutants look like, and so it is, at the moment at least, more information I think is better.
Well, I guess it really depends on how you define too much. But I mean, at the top of my head, I think so. as I was saying before in my answer, the decision process is basically based on what information you feed to the machine learning model. And as long as we're selective about the information that we're feeding to that particular model, I don't think we should particularly be too worried about the model knowing too much in a sense. So that would be my answer.
As far as my work is concerned, the work that I presented just now is mostly posed from the perspective of how the building operations manager will deal with a scenario where the building is located in an energy ecosystem that has to satisfy other stakeholders in the ecosystem as well. The problem formulation that we have performed requires mostly the operation from the building operations manager's end. And as such, it does not require too much personal information to be provided by individuals. So in the context of my work, at least, I wouldn't agree with the fact that the building knows too much. It's just that the building is operating for the greater good for all, without knowing too much about individuals present in the building.
Okay. I have another question that can go to both Bumsu and Asan. So in our previous panel, you heard quite a bit about occupancy sensing and the automation of occupancy sensing and how it can influence primarily the lighting in the room. How could your work benefit from automation of occupant information, and how could you incorporate that? So why don't we start with Bumsu?
Yes, sure. So as I described in my work, I'm basically trying to utilize passive elements in order to maximize the efficiency of any HVAC system within the building. So I guess if we were to properly detect any occupants within a certain room, I think it would actually help in terms of deciding. I guess this would actually help more in terms of the HVAC operation side rather than the utilization of passive elements. So, for example, if you have an empty room, you don't really have to have the AC on in that particular room. And yeah, in that sense, I guess it would be helpful if I were to integrate that sort of occupancy detection into my work.
Okay, and Asan?
So going back to the work that I presented, focuses primarily on minimizing energy costs and thermal regulation. What you're referring to in terms of automation and determining occupancy patterns, I see a very open research avenue in the sense that we could integrate thermal regulation, energy cost minimization, and indoor air quality management in systems, in building systems, basically, using the anticipatory results that we have for the occupancy patterns. Because obviously we know that more the number of people occupying a particular space, the carbon dioxide levels in that space would rise. So you would want an anticipatory mechanism from the control framework that we've already developed to ensure that the carbon dioxide concentration levels within a certain zone do not exceed prescribed bounds. So I see a very clear pathway to extending my existing work to include anticipatory occupancy patterns.
Okay, great, thank you. And Asan, we have another question for you. The questioner says, power is usually not a parameter that we control. Why will controlling how much power to us help with conserving it? Shouldn't we be controlling comfort parameters?
So if I were to delve into a bit more detail, what we've done is the control framework formulates the entire thermal discomfort problem that the question is referring to in terms of power. What the benefit is that generally buildings in our domain do not usually have significant computational resources. So the greater the number of knobs that are available, the more complicated the machinery that is required to execute those particular control frameworks. while yes, we are eventually meeting thermal discomfort goals, yes, what we've done is that using mathematics and convex optimization, we've been able to express zonal temperature in terms of the power consumed by individual units, so that eventually the computer or whatever computing resource that we have deals with a significantly simpler problem which has been expressed in terms of a single variable. It's more in the domain of simplifying a more complicated problem that requires meeting the objectives of multiple stakeholders in the arena. So again, to reiterate, the thermal discomfort is being minimized, but it's just that we've been able to express the entire optimization framework in terms of another variable, which is the power consumed by individual units.
Okay, thank you all. So Leah, I have reached the end of the questions in the Q&A panel.
Okay. And I can't believe we're at the end of our program. So I chatted out while the Q&A was going on the link to the Best in Show survey. I see some of you have participated in that. Go ahead if you haven't and would like to. I'm also going to put it into the Q&A box because I feel like some of you are actually using that as well. But please only respond if you are an attendee. If you are a panelist or a student, you're not allowed to vote. So this is going out right now into the Q&A as well. It should take you less than a minute to fill this out. So I hope everyone will do that and I can present results and announce the Best in Show winner, which is for a prize of $50 to the best overall. This is separate from the judges weighing in. Those results, as I mentioned, will be released tomorrow. It takes a little while for the judges to give a comprehensive evaluation, and those will be announced for our attendees to look at via our social media. If you've subscribed to our constant contacts, those will also go out. So while we are waiting for those results to come in, let's see, I'm not sure it went out into the Q&A here. John, maybe you can help me with that. It's in the chat box here. I'm going to send it directly to you.
So Leah, while you're taking a look at that, can I make a couple of comments?
Absolutely.
I really like to thank all the students for doing the work on the perfect pitch. This is kind of a unique format. It was developed by the ERC, the LESA Center for the NSF. I should say that I think that Leah mentioned the NSF actually adopted our perfect pitch practice as best practice for ERC students all over the United States. And so they do this routinely. And in their practice sessions, we had some of our past practice perfect pitch practitioners who are now employed in industry or in academia step in and help grade and judge some of the student presentations. And almost to a person, these former graduate students talked about how much they disliked the training when they had to take it as graduate students, but how valuable they found it in their careers, getting out of graduate school and actually learning how to pitch what they do in real life. So I think that's an important thing to keep in mind. And in that respect, it's been great working with them on this, and we look forward to being able to make all of you more aware of their research and how it all kind of fits together. And we just have a few more minutes left. See if there are any other questions left from the people that are attending.
Not seeing any bubble up. And Michelle, if you want to go ahead and advance to the next slide, I'm going to give just a minute more for our responses here. looks like I had a few more come in. That's fantastic. So just quickly before I announce the results, I just want to thank everybody for coming and echo what Bob said. Reach out to us, Michelle or I, our email contacts are here. If you haven't done so, please like and follow our social media. You can subscribe to our newsletter and anything that we put out to stay engaged with us. We'll be sending out more information on how EBIS comes to light, and we would like for you guys as our friends of the centers and our industry friends and our members, our LESA members, who we greatly appreciate, to stay engaged with us and let us know how we can better serve you. So without further ado, I am going to tally our results and hopefully make a very exciting announcement. So somebody want a drum roll? We have a clear winner. I'll go ahead and just drum roll. So I would like to announce our first ever Best in Show for the perfect pitches. The winner by quite a few votes was John Rawlinson.
Thank you very much.
John, if you'll dialogue with me offline, we'll talk about how we will transfer those funds to you.
Sure.
Okay. So Bob, do you have anything else to say in closing? And if not, we'll go ahead and release you back into your natural habitats, and we'll circle back with you tomorrow on our official perfect pitch winners for first, second, and third place prizes.
Thank you, Lee. I'm afraid my natural habitat is in front of a computer screen, so unfortunately. But to Will's point, when he talked about the Moss work, working with him in the LESA Center on the plant work, along with Elsa, has been, nice to get out and get back into the lab, just even for a few days. I'd like to, again, thank everybody for coming. Hopefully next year we'll be able to do this in person,
yes.
On campus, with a much broader body of people that are involved, not only including LESA, but also Case and other people on campus. If you've got any questions for me with regard to the work that we're doing and interesting concepts that you've got about what we should be looking at from an industrial management standpoint, please reach out to either Leah or Michelle or myself directly. We'd be happy to talk to you about your ideas. And of course, we appreciate your support. It's through the industry membership program that we have that we prepare a network of people to hire our students and listen to problems that are coming up in the world that help us direct our research. So again, thank you very much for your time, and look forward to interacting with you over the year ahead. Thank you.
Thank you.
Thanks, everyone.